The leak channels, they are more permeable to potassium than sodium. So, the sodium channels, they're not going to be as active as the ones for the potassium. So what we're going to see is that as we move away from the resting membrane potential, okay, the resting membrane potential is going to be dependent on ligand-gated, voltage-gated, and then our sodium-potassium pumps. Remember those? What was the purpose of our sodium-potassium pump? Because, if we think about what's going to happen, can we keep the inside of that cell at positive rather than negative, which is the resting? No, because we need to make sure that that cell returns to its resting membrane potential, because the cell has to recover. Now, as we move into the muscle and the nerve, recovery is going to become important, okay? Especially the nerve cells, but we're not that chapter yet, okay? So, muscle cells, resting membrane potential dependent mostly on the leak channels, okay? Now, when we begin to get a signal from the nerve to make the muscle contract, the ligand-gated, do you guys remember the ligand-gated? Okay, so my ligand-gated channel had little areas on it that had a specific shape, okay? The gate was closed, but if we had something that fit into it, what happened? My gate opened, and the one thing that it let rush in was what? My sodium. So sodium gets to rush in to the inside of the cell. So that was my ligand gated. If I got the ligand gated started, and then I had this one, which one was this? This was voltage gated. And if I affected the voltage, meaning I made it more positive on the inside, okay, what did that do to the gate on my voltage gated? It opened it up. And once again, the sodium gets to rush in. And then we could bring everything back to rest by way of the sodium-potassium pump. Okay, is everybody with me? All right, so now we're going to see once again our ligand-gated, our voltage-gated, and the sodium-potassium pumps. When we have an action potential arrive at that muscle fiber, and we begin to make the inside of that muscle cell, which was negative, okay, then all the positives get to rush in, all right. We changed the inside of that muscle cell to being more positive. So that tells me that my graph, if we're looking at it that way, my line is going to begin to do this number, right? Because sodium is rushing in, it's changing that electricity inside that cell. Now, at this point, when we begin to take it to being less negative, when we take it to being more positive, we depolarize. Do you guys remember that? Because we're making it less negative. Is everybody with me? And then, at some point, this line continues to do this number until we get peak action and it begins to move back down. So we go into positive, get whatever the result is supposed to be, which at this point is now muscle contraction, okay? And then we've got to make sure that all of that's positive moves out, all right? So positive has got to move out, and we've got to start turning back to being negative. So at this point, we repolarize. Does that make sense? Okay, now, with skeletal muscle, if I have, let's look at it this way, this fiber, 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 and all of those fibers making up a bundle, okay? And then we have bundles together to make up a blah, 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 okay? Is everybody with me? And then, if every single one of these has their little terminal bud attached to it, okay, which is what they're trying to show here, you know, the little nerve coming in, all right, and then it would branch and go to each one of the fibers, all right? So if I have that action potential coming down that nerve, moving into this muscle, spreading out, and going to each of those fibers, all right, chances are I'm going to have enough of that action potential to make a whole bunch of these fibers act up, okay? And in that case, if I've got a whole bunch of them that are receiving the information, chances are that muscle's going to contract. Now, here's what happens with skeletal muscle. It operates on what's called an all or none principle. Basically, if we begin to receive the action potential and it begins to move from negative going up to positive, we're going to have an area that's termed threshold. And if enough of those ions begin to move, and if we get to the right number, usually about -30, -35, okay? If we get to that number and the polarization, the muscle is going to contract no matter what. There is nothing you can do to stop that muscle contraction. So it's called an all or none principle. If you get stimulus, but it doesn't take you to threshold, that muscle's not going to contract. If we get enough stimulus and it continues taking us to more positive, more positive, more positive, more positive, we reach threshold, that's it. Boom. Whole thing's going to happen. It's going to go through the entire sequence. Muscle is going to contract and it's going to have to go into relaxation. There's no stopping it. So it is termed the all or none principle. When we look at the structure of the muscle fiber, what do you kind of notice? Does it look kind of weird? Now, remember, these are termed sarco, okay? We've got a sarcomere, okay? The liquidy inside the cell stuff is termed sarcoplasm, okay? Which is another term for cytoplasm, okay? We have a sarcoplasm that, sarcoplasmic reticulum, okay? Had to get my term straight, okay? Which part of this do you think is maybe what we think of, that's the equal to the endoplasmic reticulum in a cell, okay? What part of this structure do you think is the sarcoplasmic reticulum? It's all this webby looking stuff. Can everybody see what I'm pointing to? So that's my sarcoplasmic reticulum. Looks kind of weird, right? Not what we would think about for the reticulum, because we think of the endoplasmic reticulum, we think of rough and smooth, where we had like ribosomes or no ribosomes, right? This right here is just sarcoplasmic reticulum, this webby looking stuff. But now I've got what looks like to be something that invaginates into this bundle, and then see how it kind of looks like it invaginates into the bundle, but then it looks like it's invaginating right through each one of these fibers at an area that's the boundary for the sarcomere. Is everybody following me? So the structure is a little weird, right? Let's think about this, okay? Remember, this is going to be part of a fiber that's long, okay? And that fiber is going to have its innervation. But that innervation is only going to be at one point on the fiber. So if I've got a fiber this long, okay, and I've got the nerve coming into it, that means in this entire length, it's only innervated at that one point. I now have to make sure that this action potential, this signal, travels the entire length of the fiber, because I've got to make sure that for contractions to take place, every single sarcomere shortens, but not every single sarcomere is connected directly to the nerve. Does that make sense? So I'm now going to have to make sure that this action potential passes along the fiber, propagates. That propagation occurs. Is everybody with me? Yes, no, maybe. Stop me now. Okay.